I'd like to take a look at some trigonometric identities. An identity is an equation that is true for every value of the variable. We can use identities in trigonometry to describe some characteristics of the trigonometric functions. We've seen some of these already. In particular, sine of theta is the reciprocal of cosecant, and cosine of theta is the reciprocal of secant. Also, tangent of theta is the reciprocal of cotangent. So these reciprocal identities, these are identities because they're true for every possible angle. And there are others as well. We talked about cofunction identities, and we also talked about more recently even and odd identities that say things like sine of negative x equals negative sine of x because sine is an odd function, and cosine of negative x equals just positive cosine of x because cosine is even. So these identities can be used to describe some important and somewhat useful relationships among trigonometric functions. What I'd like to talk about in this video are some new identities that come from the unit circle. For any point on the unit circle, the coordinates x and y correspond to cosine and sine values of an angle. And we also know that tangent is the ratio of y over x. And so making a pretty simple substitution, we can see that tangent is the same as sine of theta over cosine of theta. Because of the reciprocal relationship we saw a moment ago, that means that cotangent is the same as cosine of theta over sine of theta. And this is actually really nice because it means that all of the trigonometric functions can be expressed in terms of sines and cosines. Because we can add to this list, I could add that secant of theta, of course, is equal to 1 over cosine, and cosecant of theta is equal to 1 over sine. We're about to talk about some problems related to simplification, and being able to express every trigonometric function in terms of sine and cosine has some really nice benefits in terms of simplifying trigonometric expressions. Now, because the unit circle is centered at the origin, any point on the circle, the x and y coordinates have to satisfy the relationship x squared plus y squared equals the radius squared, but of course that's just 1, because 1 squared equals 1. But we also just mentioned that the x coordinate and the y coordinate are associated with sine and cosine of some angle. And so for any angle, it has to be true that cosine of that angle squared plus sine of that angle squared has to equal 1. And we call this the Pythagorean identity because it relates to the Pythagorean theorem. So a comment about notation: exponents for sine and cosine are often written in the following way. So for example, cosine of theta squared, that means cosine of theta times cosine of theta. For the cosine and sine and other trig functions, we often write this as cosine with a little square next to the s of theta. And so the Pythagorean identity could be written in that notation in the following way. So it would be cosine squared of theta plus sine squared of theta equals 1. So this is the more standard notation for squaring a trigonometric function. Let's look at an example of how we can use these trigonometric identities to simplify expressions. Let's try to simplify the expression cosine of x over 1 plus sine of x plus tangent of x. There are a few different things we could do to get started. I'd like to think of this as a pair of fractions, which it doesn't look like that at this point, but we can kind of think of it that way because tangent, as we saw a moment ago, is the same as sine of x over cosine of x. So I can substitute for tangent of x using the identity tangent of x equals sine of x over cosine of x. Well, now let's think about these fractions. I can put them together by multiplying to create a common denominator. So in the second fraction, I want to multiply by the denominator of the first. So I can multiply this by 1 plus sine of x. But then I also want to multiply the top by that same thing. Over here, I want to multiply this side by the denominator of the second fraction. So I'm going to multiply the bottom by cosine of x, and I'm going to multiply the top by the same thing. So I can think of the first fraction now, it's cosine squared of x over cosine of x times 1 plus sine of x. And the second fraction is sine of x times 1 plus sine of x divided by cosine of x times 1 plus sine of x. And so thinking about the step that we did to get there, I found a common denominator. Well, next let's add the fractions. So adding fractions, adding rational expressions like this, I want to add the numerators together. And so I have cosine squared x plus, well, over here as I add it, let me multiply it out. So I have sine of x times 1 plus sine of x times sine of x, so that's sine squared of x. All of that is over cosine of x times 1 plus sine of x. So at this point, let's think about what we can do. I have a cosine squared and I have a sine squared. And we just said a moment ago that the Pythagorean identity is sine squared plus cosine squared equals 1. That means that these two terms together equal 1. And so the Pythagorean identity can make sort of big jumps in simplification. The numerator is really the same as 1 plus sine of x. But notice that we also have a 1 plus sine of x in the denominator. And so those are both factors of everything. The 1 plus sine of x up top, the 1 plus sine of x, that's a factor of the numerator. This is a factor of the denominator. And so I can cancel those two common factors. So we end up simply with 1 over cosine of x, which is, we know, the same as secant. And so our original expression became much, much simpler because of some of the trigonometric relationships we know. And this is a statement that's true for every angle. So this expression, for every angle where this expression is defined, that's the same as the value of secant x, wherever it is defined. So let me end with just some additional comments about the Pythagorean identity. We can actually think of the Pythagorean identity as a set of identities. We've seen that sine squared x plus cosine squared x equals 1. If we divide each of these terms by cosine squared x, we get the statement tangent squared x plus 1 equals secant squared. And if we divide that original statement, if we divide each term by sine squared, we get 1 plus cotangent squared x equals cosecant squared x. And so I'd encourage you to check that, take a few minutes, and make sure that you kind of see the connection between that initial statement of the Pythagorean identity and these alternative forms, and verify that that's true. Well, I hope you enjoyed the video. Thanks for watching.